Hi, in this video, I'm going to cover Chapter 6 of the Grokking Deep Reinforcement Learning book from Miguel Morales. In last chapter, we covered Chapter 5 in the last video, in which focus on improving the value function. In this chapter is focused on improving the behavior, which is related to the policy. So various algorithms are going to be shown. Some of them are better than others. We're going to compare them, compare the differences between them. And these are the algorithms shown in this video are basic. In the next chapter, chapter 7, it goes in the same line, but with more advanced and more efficient algorithms. Okay, so here's the chapter, chapter 6. I'm going to put the links of the examples in the video. And if you want to go more details, I recommend getting the book. Okay, so let's go to the example. First, we have to import the libraries needed. That's reinforcement learning gym and NumPy and other things. Nothing from deep learning yet. That's gonna come later. I'm still in this chapter and the next one. I'm using the Jupyter notebook, but for chapter 8 and forward, I'm gonna use VS Code because it allows better to debug and understand better. But for this example, it's not much necessary. Okay, so this is for plotting, and I'm going to go into it. We're gonna go first through a set of utility methods. And then we're gonna go through the different algorithms and compare the differences. And at the end, we're gonna run those algorithms with different environments of increasing complexity and compare the efficiency of each of them. We're gonna see the advantages. Okay, so starting the value function is gonna give us the real value function. Okay, so in here, in this video, in these examples, the author is using toy examples. Because of that, we can go exhaustively through all the data of the environment and compute the real value function, and therefore the real optimal policy and the optimal queue. Okay, so yeah, if you have any trouble running this, watch the first video on this series. You can have the details there of how to set up the environment. Okay, so this is the baseline. So with this one, for each environment, we run this and get the optimal values for comparison. So you can see here that it's going to go through P, which is environment. It's going to create zeros for Q, and it's going to go through all the states on the environment, all the actions, and all the actions of the environment, states and actions, are going to have a probability of going to one state or another, and they're going to have a reward. That probability is multiplied by the long-term reward, which is the immediate reward, and the estimated long-term reward by the decay factor. And of course, if you're done, you don't consider long-term reward, just the immediate reward. Okay, so basically it's averaging everything. And with this, we're gonna get the true Q function. And then from the Q function, you take the maximum of the actions, and that's your value function. And then you have a lambda that takes the argmax of the Q function, and that's taking the maximum action, and that's your policy. Basically, it's taking the action that maximizes the Q. That's your optimal policy. Okay, so what's gonna do is gonna compute here the value function in the moment and compare it against the value function that you already have, which is set at the end of the iteration. And if it is below a threshold, then you're done. Is stabilized, the learning is stabilized, and then you have your value function, and that's what it's gonna do. Okay, so that's for your baseline. So we're not gonna need to print the policy, and this for each state is gonna print the action, which is basically your policy, and this is to print the state value, which is the value function. You're gonna print the state and the corresponding value to visualize the values of the v function, the value, and then the same thing for the action. For each state, print every action. You concatenate the q function here to the state, and then if you have an optimal q, then you have a compute the difference in a tabular manner. We're gonna see it. Actually, we can just go ahead and see it. So basically, that's gonna print this. You're gonna have the q function for each action. What is the expected long-term reward, and for each state. And here you're printing the state value function, which is for each state, give me the value for that state. And also this is the policy printed. You see that you use a symbol, and for each state, what action the policy is taken. So basically those are what the functions are doing there. Okay. Okay, so let's go. Then this is to get the policy matrix. What it's gonna do is simulate the policy. And basically it's going to go through all the episodes. It's going to evaluate, this is your policy. Given the state, give me the action. And then you're going to evaluate it in the environment here. It's going to use that action also to get the from the optimal queue. It's going to take the maximum and then evaluate that action in your mole, in the queue function, to take the difference and compute the regret and accumulate the regret in the last element. So everything is put in the last element. So you take the action, get the reward from the environment, and put it into, accumulate it into the last element. So you can see that the action is going through all the trajectory of the episode and accumulating the reward. And finally, that's gonna be your metric. And then at the end, it takes the average of the rewards. And at the end, if you reach the end of the trajectory, if you're done, then if you read the goal state, then that's a plus. And you take the average time of that you reach to the end, or the average, I mean, take the percentage of times that you reach to the goal in the trajectory. So that will be the success, the reward, and the regret. So those are your metrics. And then the next method is gonna just go through a trajectory of a set of uh, policies and just get the metrics and just compute it. Is this an aggregate wrapper of the previous one? So you're gonna need the root mean square to compute the difference between two values for evaluation, and the moving average is basically facilitate the the display of the data. Is basically it takes a sequence, and the sequence is going to be transformed in such a way that each element is going to have the average of the previous n values. That's about it. It's something very simple. There's some array arithmetic in there that is done to compute that in an efficient way, but I'm not going to go into that. Similar to this one, this is for plotting, visualization. I'm not going to go into details. And this one, the only thing important about the decay schedule is that it's going to be a logarithm that's going to go down. You see that it's just log space. So at the end, this delay schedule is going to look like this. And this is used for the learning rate because the learning rate is going to drop. The alpha is going to drop from 0.5 to almost 0. So at the beginning, you will learn a lot and then slow the learning down. Similar to exploration, epsilon is for exploration. You start at 1, so you do maximum exploration at the beginning, and eventually you get greedy. So that's the purpose of the decay function here. Okay, so we're done with libraries that we're going to use. Now we're going to go to environment. The first environment is Sleepy Walk 7, which is this one. So you have a linear set of states. You go from 0 to 8, and you want to go to 8. So you're gonna get, you can imagine that you're gonna get better rewards for going right. So when you take an action, let's say you want to go right, there's gonna be a probability of going back or staying in the same state. And you can see it uh, when you create the environment, you can take the P in here, and the P is the one that we're gonna use. There's some other parameters like the gamma, number of episodes. The goal state is the 8, the final state, this one. So yeah, those are other parameters. So let's run it, but first, let's take a look at inside of it. Let's just print it. And you can see that we have 8 states. And this is the goal states. When you reach here, this is a terminal state. So it has true in the terminal field. And you just stay in number 8. And if you're in number 7 and you go right, you have two actions. Go left, go right. And the right, if you land in 8, you got a reward of 1. The other ones get 0. So you get 0 if you don't get to the goal state. And if you get to the goal state, you get reward of 1. Okay, so that's basically a state. It's very simple environment, but we're going to try more complicated environments later. And the beauty of this is that these algorithms are ready for any environment. So when you see things like, okay, I'm getting the argmax of the queue or getting the maximum queue. So that is very agnostic to what the action is. It's just taking the action based on the queue function. So it can be an environment with one dimension or a two-dimensional environment like the frozen lake that we're going to see later. So that's very convenient for evaluating these agents because we can just plug and play different environments to evaluate the performance on more complicated environments. So that's exactly what we're going to do in this example. Okay, so let's visualize the decay schedule. This is again what I mentioned. This is for the learning rate and exploration. So it's not necessary to go much into detail that, just that they are going to decay. Okay, so now we're going to use the value iteration function that I mentioned earlier to get the optimal queue, optimal value, and optimal value function and optimal policy. We're going to get the value, display the value function, display the action value, display the policy, and the metrics. The metrics are obtained here, get goal metrics. So we're going to do all of this, we're going to do it for all the agents that we see. This is going to be our baseline. So you can see in here that the farther you reach to the right, you get a higher reward, expected long-term reward, and the farther to the left, far from the goal, is less. And of course, the action, you can see that you're gonna get a better reward if you take the right, because the optimal policy, as you can imagine, is always go right in this very simple environment. And you get 96% of success and average of 0.85. This is not very important because this doesn't vary much through all the agents. What is important is that you get a good estimate of the value function and you get a good estimate of the Q function. And that's what we're going to compare between the different agents. Okay, first, let's go to Monte Carlo. Monte Carlo is a very simple agent, but what it does is basically go through all the whole episode, get the experiences, and once the episode is finished, it's gonna take all the experience point from that episode and it's gonna train it's gonna train the Q function with that, and it's not very accurate as we're gonna see later. It works, but it's not the it's one of the worst algorithms for training the Q function. So since we are we want to get all the experiences before training the queue, we need this function to get all the experience point. So what it's gonna do is gonna reset the environment. It's gonna select an action based on what this is the lambda that we're passing, and this lambda is gonna use the epsilon to say, okay, I randomly take an action, or I take the argmax. I take the greedy action, either the greedy or the exploration. Once I take the action, I evaluate it in the environment, and that gives me the reward. And from the reward, I assemble the experience point, which is the current state, the current action taken, the reward, the next state, and if it is the end of the episode. So that's an experience point that is appended into the trajectory. So the trajectory is a set of experience points. And then if I reach done, then I'm done. But if I count beyond a certain threshold, I say, okay, I did not reach the goal. I mean the end. So what I'm gonna do is clear the trajectory, break, start all over again, and then I'm gonna keep repeating this process until I get a trajectory that goes from start until the end of a formal end of the episode. And then I return that. Okay, so we're gonna pay a little closer attention to the Monte Carlo because all the rest of the agents are going to be almost exactly the same, just with a little difference. After this one, we're going to just evaluate the small difference between the algorithms. Okay, so here you have an observation space that is determined by the environment. You can see here that it's taking the observation space and the action space. So from that, you infer the number of states and the number of actions. Then you have the discounts because the reward can decrease as the number of steps go in an episode. So it's gonna start with 1 and then it's gonna go 0.99 or something like that. And just notice that it's gonna use a log space. It's not gonna use the decay schedule, but the decay schedule also use log space internally. But it's gonna decay from one point to another. So that way you decrease the reward. The alphas is the learning rate, the curve that we just saw above, and epsilons is for exploration. So you have to create the Q function empty with zeros. Number of is basically the state space and the action space. And then you have to, this Q track is just a collection of Qs for each episode so that you can plot it later. Okay, this lambda is important. This is the one that is going to be used for selecting the action. So if you're going to select randomly a number, and if it is above the epsilon, this is the logarithmic decaying factor that starts in 1 and ends up almost in 0. So at the beginning, it's going to be very probable that this is false. And because of that, it's going to be randomly selecting an action based on the action space. It's going to take one action randomly. Then as time goes by, this is going to be less probable and it's going to be more probable and it's going to be true. So you're going to take the argmax of the Q function. This is the greedy action. So that's basically this lambda what it's doing. It's doing either taking the action, either exploratory or greedy. Okay, now first we're gonna iterate through all the episodes, and in Monte Carlo, you're gonna generate a trajectory. So beforehand, you get all the experience points, and then you work on those experience points for that episode. So then we have an extra array to see if an experience points have been visited. I think we saw this in the previous video, that sometimes we don't want to consider the state more than once. So you have a parameter here saying, okay, if this is on, then I'm not gonna consider the experience point more than once, and you can see it in here. So it's gonna go through all the experience points in the trajectory. And if this is your first visit, if this is cleared, then you're gonna, if this is on and the state and action has already been visited, ignore it. If it has not been visited, then you set it to 1. So in the next one, you don't visit. And we saw in the previous video that it is more efficient when this is true. So now we're just going to evaluate it with true. You see this Monte Carlo here where we're going to call it. And we just take the default value, which is true. So yeah, we're only going to visit the state ones, the experience point ones. Okay, so from that, it's going to just compute the long-term reward directly from the current experience point until the end of the trajectory. And notice, imagine that you have 5 experience points. What this is going to do is that it's going to say, okay, at the beginning, I'm gonna take all the experience points from 1 to 5 to compute the long-term reward. Then on the second iteration, I'm going to go from 2 to 5. And the third iteration, I'm going to go from 3 to 5 and from 4 to 5. That's why it has to clamp the discounts to match the number of experience points. And with this, I get the G, which is the long-term reward. And with the long-term reward, I just get the difference with the Q function and use the alpha, which is the learning rate, to update the Q. This is a very simple learning function. When we go to deep learning in next chapters, it's going to use something like adaptive momentum or any other deep learning algorithm. But this is a very basic one. Okay, so that's how you train the Q function, basically using the experience points. And finally, we keep the Q for the plotting, and then from the Q, we infer the value function like we did in the optimal case, taking the maximum Q value for each state gives us the value function, and then we take the argmax of the Q function, and with that we get the optimal action based on the Q. So that's our policy. So we infer the policy, the value function, and we return it along with the Q. So that's Monte Carlo. Now what we're going to do is run the Monte Carlo with environment, with the gamma settings and number of episodes. And we're going to run it a few times for each seat. We have like 5 seats. So we're going to run it for 5 seats and take the average of those seats. You see the mean here. We take the average and display it. So let's run it. And now we're going to run this is the same functions that we run for the optimal value. Printing the state value, we're going to compare it against the optimal. This is from Monte Carlo. We're going to compare it against the optimal, take the difference, and again, print the value function and print the policy and take the root mean square difference between the Q function and the optimal Q. And same thing here. We take the root mean square error between the value function and the optimal Q. And this difference between the agent value and Q functions are taken against the optimal value and Q functions for each agent so that we can compare them. So let's run it, and we can see that the difference for the Monte Carlo first visit Monte Carlo is 0.293 for the value function, and for the Q function is 0.0486. Now these numbers are the ones that we're going to use to compare against other environments. Okay, now the next agents. Okay, so the next one is SARSA. SARSA doesn't it's gonna do something more common that we see in learning, in reinforcement learning, which is updating the queue function for each experience point. It doesn't wait until the end of the episode to train the queue function. It does it for every state. This is still not optimal, but it's going into the direction of the optimal algorithms. Okay, again, it's gonna set up the queue, it's gonna set the alpha, the epsilon, all of this is the same. But notice that we enter into the episode and reset the environment, select the action, and then we enter into a for loop. So we evaluate the action in the environment and get the experience point. And with that experience point, we're gonna update the queue function. And we do it by estimating the long-term reward. We need to calculate the expected long-term reward, and that is taken from the actual reward that is given directly from the environment and the long-term reward, which is using the queue. So basically notice that the next action, which is taken from the policy, we're basically training the policy and training the queue with the same and using those same things to compute the long-term reward. This is not very stable and not very optimal because it's like eating the same dog food. I mean, it's like basically training. It's like a circular training. It's not very good. So we're gonna see different techniques that are gonna improve over this. So yeah, the same queue function that is trained is used to estimate the long-term reward. So you get the next action, and with that, you estimate the remaining rewards. Put the gamma into it to decay it, and of course, I do not include it if this is the final step of the episode. So with that, we take the expected long-term reward and the difference between it and the queue function, you multiply by the learning rate and you update the queue. And that's it. And infer the value function, infer the pi. So that's a difference between the Monte Carlo and this one. This is training the queue function for every experience point that we get from the environment. Okay. So that's the SARSA. And now let's try out the SARSA. Again, we're averaging over all the seats. And now we're going to run it. We're going to run it and see how it goes. And you can see that we got 0.0467 for the value function. And let's see what we got in first visit Monte Carlo. Actually, first visit Monte Carlo is better than SARSA. And also the Q function is 0.486. So yeah, definitely first visit Monte Carlo beat SARSA. But SARSA is going in the direction of Q-learning. And Q-learning is going to beat significantly both of them. So let's see what Q-learning has differently. So initially it's the same as SARSA. It's going to get the alphas for learning, the exploration rate, and the action, the policy is using the argmax or the random exploration. This is the same, all the same. So it's going to take the same, go into the episode, take the action, and for each action, it's going to update the Q function like the SARSA. But notice a big difference in the Q function. Instead of using the next state from the poll, it's going to use the next state from the no, my bad. It's still using the Q function to estimate the long-term reward. But instead of using the policy that we have is going to take the argmax of the Q function. So something different is guiding the estimation of the long-term reward rather than the own policy that you're training. So you remove some of the circularity that we have in the previous agent. And just by doing that, you're going to see the big difference. That's the only difference. And then again, you get the difference between long-term reward and the Q function and update with the alpha the same way and infer the value and the pi. So with that, we're going to run it, average it over the seats, and print all the value functions, the Q functions. And we're going to see the value function error, root mean square error, is 0.0049. That's about 10 times. The one for first visit Monte Carlo was 0.0293. So it's like 10 times more efficient, more accurate. And for the case of this one, the Monte Carlo, first visit Monte Carlo was 0.0486. So again, it's like 10 times more accurate, the Q function. Just by updating the Q function for each action, and also using the argmax rather than the pi function. Those are the two main differences with first visit Monte Carlo. Now, double Q learning is the final agent that we're going to present in this video, and it's a little bit more complicated, and sometimes it's more accurate, but not than Q learning, but not by much than the Q learning, yeah, but not by much. Sometimes it could help, and the difference in here is that it's going to use a couple of Qs, and the final Q function is going to be the average of both. So you can see here that when selecting the action, it's going to be based on the Q, but you take the average of the two Qs, and with that you select the action. Then when you train, you don't train both at the same time. So it's trying to give some stability. This is similar to what we're going to see in later chapters of having a target network that is not updated frequently, but it's used to estimate the long-term reward. But the real Q function is updated in all steps. But then at a given cadence, the target Q function is updated. So this is something similar. It goes along those lines. Randomly pick up one of the two Qs, and one Q is going to be used to get the Rmax, the action, and with that, you evaluate it on the other Q. So the other Q is used to estimate the long-term reward, but the Q where the action was taken is used to select the Q of the other Q, and then update the Q1, and vice versa. And here the other Q takes the other role for taking the action and the Q, and you can imagine that this could be improved if instead of using this cube, because looks circular like the SARSA, so one thing that you probably can do to improve it is take the argmax of this one, and that would be more independent. That could give the same advantage that Q-learning had over the SARSA. So by taking the argmax here, it might even improve over the Q, but probably because this is introducing some circularity, it didn't perform as good as the Q-learning. So we're gonna see it. So that's the difference. At the end, you take the average for getting the pi, take the average again to get the Q, and from the Q determine the value function, and that's it. Okay, so now let's run it over the seeds, take the average, and it takes a while. I'm gonna pause the video. Okay, finish. So let's run it to see how good it is. So it went down from 0.0049 to 0.0046, so the difference is very small. So it improves very slightly the value function, but it got worse, a little bit worse in the Q function. You see the Q function got a little bit worse. So because of the added complexity and the performance not very convincing, it might be better to stick with Q learning sometimes. So let's now evaluate, let's take a closer look at this. So you can see that the Monte Carlo does very good on the states that are close to the goal, but the farther you are from the goal, the farther away. You can see these dark lines are the optimal value. And you can see that it basically gets to the final state at 1,500 episodes. And something similar, we're gonna see, this is a closer look, you can see the instability of the Monte Carlo. So we're gonna compare that against the SARSA. You can see the SARSA that around 1,500 gets stabilized and also exhibits the same problem being far from the goal, from the actual value as when you're far from the goal and closer to a goal. So it's kind of more stable, but it has more separation in here. Monte Carlo is closer, but more unstable, a little bit more unstable. Almost the same. Both of them are bad anyway. Okay, so you can see that it's more stable learning because SARSA is learning experience point by experience point rather than taking everything at once. So it's more stable in learning. Okay, so let's take a look at Q-learning. Q-learning looks way much better. It converges faster around 1,000 episodes, 500 episodes less. It learns faster basically. And you can see that the values outside of far from the goal are learned correctly. And yeah, definitely it's more stable. Maybe not that much, but it works better. In double Q learning, you can see similar results. Double Q-learning is not that far from Q-learning. Okay, so you can see that it looks a little better, a little more stable, perhaps. So let's see how they perform in other environments. So we started working. I'm gonna skip all this. You can this link you have it in the description of this video. You can explore in more detail. So now let's take a Russell Norvig example. So we saw this one, a very simple example, slippery walk 7. So now we're gonna take a Russell Norvig, which is this one. This is Russell Norvig. It's basically a 3x4 environment. It's a little bit more complicated. So as I mentioned before, these algorithms are ready for any environment. That's the beauty of it. And okay, so we create the Russell Norvig. Perhaps we can take a look at the environment, and you're gonna see that it has 12 states, and the goal state is gonna be 3. And you can see that it has 4 actions going up, down, left, right, and number 3 is the goal state. You can see that you have it here, and if you even by accident arrive to state 3, then you have a reward of 1. Otherwise, you have a negative reward in here. So that's your environment. Okay, so now again, this is the decay schedules. And now I'm getting the optimal values, optimal Q, optimal B, and optimal pi for the Russell Norvig environment. So yeah, we first visit Monte Carlo and see what that gives us. Okay, so in here you can see that Monte Carlo is being passed the Russell Norvig environment, an average. So let's see what it gives us. It's going to be 0.1995 for the value function, and for the Q function, 0.35. Okay, now let's compare against SARSA, and there's no much expectation on SARSA. This is SARSA and the environment. So let's run it. And you can see that SARSA is pretty bad, 0.28 versus 0.19 on the value function, and almost more than twice on the Q function. So it's very bad. So let's take a look at the Q learning with Russell Norvig. Okay, we're running, and let's run this. And you can see that it is again 10 times more accurate than the first visit Monte Carlo. And the same goes for the Q function. So far we have the best is 0.0225 and 0.0243. Now let's go to double Q learning. Let's run double Q learning. It's taking a while. I'm gonna pause. No, it's finished. Okay, so let's run it. So again, like in the 7 slippery walk 7 is slightly better in the value function, but it's worse. I would say significantly worse, because I think it was 0.024 something in the Q function for Q learning, and this is almost twice. So again, the extra complexity of double Q learning is not just being justified in these 2 environments that we have seen so far, but maybe if you have a more complicated environments than the toy examples in here, it might be justified. But again, the double Q learning, it can be improved, and that's what we're gonna see in the next chapter. We're gonna see better agents. Okay, so let's go straight to the last environment, which is the frozen lake. Frozen lake is this one. It's 4x4. It's even more complicated to see if the story changes there. Okay, so let's go to that environment. Frozen lake. Okay, it's a 4x4. It's similar to the Russell Norvig, but even bigger. So again, let's run this and get the optimal Q, optimal pi. Let's run Monte Carlo. And with that, I'm gonna pause the video because this is a bigger environment, so it's gonna take longer to execute. So I'm gonna have to pause. Okay, so I run this and 0.19 for Monte Carlo and 0.18. Okay, 0.19 and 0.18. Okay, let's run SARSA with this. I don't expect much from SARSA on this one. Okay, remember SARSA was kind of circular, but actually in this one it matched 0.19 the first visit Monte Carlo. and 0.17. So it improved. In this one, SARSA beat first visit Monte Carlo. Okay, so now let's go to Q-learning, which has been consistently beating the other two in the other two environments. Let's see how it does in here. Okay, let's see how it does. Yeah, point. So it's again 10 times more accurate in the value function and 10 times more accurate in the around more probably more than 10 times more accurate on the Q function as well. So okay, our uh, best numbers now for value function is 0.0156 and 0.013. Let's see how double Q learning is doing for this one. It's gonna take longer to train. Okay, so now let's see how it goes. So Q learning was 0.015 something, and this is way over that. And for the Q function, I don't, it was 0.13, so it's really bad. So the double Q learning didn't work well, and as we saw, it has the property of circularity. Instead of taking the argmax, maybe you could have done better like that. But so far, the Q learning function and the difference between Q learning is almost the same as SARSA, but the difference, as you saw, is that instead of taking the action to estimate the long-term reward from the policy, it takes it from the argmax of the same Q function. That's it. It's very simple. Okay. So one more curiosity is how long it takes to converge. You see that the first visit Monte Carlo, it does pretty bad in terms of estimating. And when we go to a Q function, the SARSA does equally bad, but when we go to a Q function, it in relatively fast it learns it. And the double Q, it took around 4,000 episodes, and we go to double Q learning. Oh, it takes. As you can see, the double Q learning what offers is the stability because of having the two Q values. But again, it's a little bit circular, but still, it has some promise. So in the next episode, we're gonna go through different, more efficient agents that are gonna beat the performance that we have seen in this video. Thank you very much for watching.